one thing that functions do for us in general is they give us a way of sort of transporting things from the domain to the codomain, right? So if this is our domain and we have some subset of the domain S, so maybe this is S here, and we have the codomain over here, right? The function sort of gives you some way of transporting everything from the domain to the codomain, right? So this is F. And if you have this subset S, well, the function is going to transport S to some smaller collection inside the codomain. And this smaller collection that S gets sent to, this is called the image of S. Put my F next to O. There we go. So this is called the image of S. You can kind of see the inspiration for the term image. It's just because it's as if F is doing some sort of image processing and sort of projecting, sort of gathering information about S and projecting it onto the codomain somehow. So that's the origin of the term image. To write down what the image is sort of precisely as a set, you'd write it this way. So first of all, the notation for the image is just F of a set. And we're using the same notation for image as we are for evaluating a function, which can be problematic. So you have to be careful now that we might use this notation. You have to keep track of, when we're putting something into parentheses next to a function, you have to know, are we evaluating this function, or is this thing a set of elements from the domain and we're talking about the image of that set? But the image is just everything in the codomain where something in the domain gets mapped to that element in the codomain. So, right, y in this expression here, y lives over here, right? And there is some x on the domain side that the function sends to y, right? So the image is just everything that gets hit by something in S, basically. Now this is for any function in general. If we're talking specifically about a linear map, then things get a little better, because it turns out that the image of any subspace is a subspace of your codomain. This isn't very hard to show, because if we have W1 and we need to write down a subspace first. So let's say that S in V is a subspace, right? To show that its image is a subspace of W, we just have to show that it's closed under linear combinations of two elements. So let's take two elements in the image, so say W1 and W2 in the image of S. Okay, we need to know, is any linear combination of W1 and W2 in the image of S. Okay, well, W1 and W2 are in the image of S. This implies that there are V1 and V2 in S, so that f of V1 is W1 and f of V2 is W2. Right, so this is just a fancy way of saying, since W1 and W2 are in the image, they have to get hit by something, right? So now we need to produce some element of S so that F turns that into this linear combination of W1 and W2. Well, let's consider this linear combination, AV1 plus A2V2. Now this has to be an S, because S is a subspace. Right? V1 and V2 are both in S, so S has to be closed under linear combinations, so AV1 plus AV2 has to be in S. All right, well now let's see, what does F do to A1V1 plus A2V2? Well, we're assuming F is a linear map, so we can use preservation of structure to rewrite this as A1F of V1 plus A2F of V2, but that's A1W1 plus A2W2, right? So what we did is we showed that any linear combination of two vectors in the image gets hit by something from S. This shows that A1W1 plus A2W2 is in the image of S. So, right, and this shows closure of the image. So this means that the image of S is a subspace. All right. So that's sort of interesting in general, but there's one particular example of this that's especially important, and that is the image of the entire domain space. So we will say that for any linear map, the image of the map, so not the image of a subset, but the image of F itself, is the image of the entire domain space. And again, some people call this the range, but I'll try to be consistent and call this the image. So this is image F. Of course, the image of this linear map F is the same thing as the image under F of, sorry, I should write it this way, the image under F of the entire space V, which is just everything in W that gets hit by something from V. And because of what we just proved about the image of a subspace being a subspace, the image of the map is a subspace of the codomain, right? V is a subspace of itself, so the image of V has to be a subspace of W. And we will call the dimension of this image the rank of a linear map. Okay, so the rank of F is just the dimension of the image of F.